All right. That was the previous one. We are going right in order. So for energy and thermodynamics, we're just identifying this. Now, C, we didn't really talk about in class. I will tell you right now, it is what we call the activated complex. All right. Now, the activated complex is just the point at which our reaction begins to then progress. So you don't have to worry about C, but I put it there just because it's a part of this type of potential energy diagram. But the other parts are the more important parts. So at part A, this is the energy of the reactants. Right, and this is like the progression of a chemical reaction, right? So you start with your reactants, and then you have to end, of course, at the products. So that D portion is the energy of the products, right? So that's your start and that's your finish. Now, where are the other two? Well, let's talk about E really quick because that compares energy of the reactants to energy of the products, right? And no matter where A is compared to D, that's what this E portion will represent. So when you're talking about it, this energy, this potential energy, we're also calling it thermal energy in this unit. So this is our heat. And what this tells us is that from start to finish, there is a change in that heat energy, right? So this is change in heat, and we label that as delta H, right? Change in heat, delta H. And that's why this down here should actually be delta H as well. All right, which letter? That's E. And then B, right? So think about this as like a little roller coaster. If you've ever been on a roller coaster, here is the cart, and here is maybe you. And you are, in order to go through this roller coaster, you need to go all the way up to the top in order to then progress through, right? Well, these chemical reactions are no different, right? They need to start at a certain spot and then get to a certain point with a certain amount of energy before they're able to then progress through. And so we say that it requires this activation energy, or E little a. And activation energy is from the start to wherever the top of this is. And so I like using the roller coaster analogy because it's true that you wouldn't be able to get through the rest of the ride if you don't get through the very top part, right? From start to top. So the activation energy is just the amount of energy that's needed to get this going, right? So that's the idea here. Endo or exothermic, remember, endo means absorb energy. Exo means lose or release it. And you can use these diagrams to figure out which is which by just seeing, am I starting with more or less energy than what I'm ending with? So I'm kind of just using the comparison between A and D here. In this case, you see that D is lower than A, which means I lost energy, right? So if I'm losing energy, we say energy lost. That means that this is an exothermic, right? It's released. So we say exothermic. And how we actually would introduce that by the change in heat is that there's a negative change in heat because it's being lost. Now, if I had something that looked a little bit more like this, well, this is the activation energy here to here. And then this right here to here would be the change in heat, right? Here's our reactants, here's our products, and then in this case, this would be endo, and it'd be endo because my products end with more energy, right? So I'm gaining energy, so this delta H would be positive. That's the difference between those two right there. Given the following, identify the following. Here's how I like to look at this, all right? Knowing that there are three states of matter primarily that we talk about, and there's three parts of this that are curved upward. So from A to B, C to D, and E to F, those are all of our states of matter, right? So this is where something is completely solid, this is where something is completely liquid, and this is where something is completely gas, right? And because temperature is, by definition, a measure of average kinetic energy, anytime the temperature is changing, the kinetic energy is changing, right? So this tells me, if I'm a solid here, that kinetic energy is changing as I heat or cool that substance, which tells me that the particle speed changes. Okay? And this idea holds true at each of these points where there is a particular state of matter. So here, the kinetic energy, it's changing, and then it's the same thing over here, right? So the change in kinetic energy, the speed, change in kinetic energy, speed, change in kinetic energy, speed. Right? There's a theme here. When temperature's changing, the speed changes. So in order for us to, let's say we're adding heat, and in this case we are, because this is a heating curve since the temperature is rising, right? And as we add heat over time consistently, we see that there's these instances where these states of matter exist, where we need to get the particles to start moving a certain speed before they're able to enter that next step. Well, we also notice that there's these portions right here that are flat, where there is no temperature change, and therefore something else must be happening. And at these parts, we say that there is a phase change occurring, right? So what happens at these parts is that realistically, there is at this point solid and liquid at the same time. And so what's happening is, at this point, it's 100% solid, this substance, and usually we talk about this with water because that's easier to look at. This is 100% solid, but the particles have gotten to a speed where they can no longer go faster until they spread out further away from each other. So at these points right here, at these phase changes, there's a change in potential energy, right? Which means that instead of the particle speed changing, the particle space changes, right? And the idea is that the this potential energy gets those it will weaken as this gets heated up and these particles move further and further away from each other. So this is again what we call a phase change, right? And we'll label exactly what those changes are here in a sec, but that's our nice little description there. And then of course then at this point it's fairly similar, where now there's liquid and gas existing at the same time, because at that point the heat energy that we're adding is causing the potential energy to change, not the kinetic. And that means that the spacing will change between those. So then what are those things? Well, let's talk about what it's called when they're heating up first, right? What are those phase changes? Well, of course, it's melting, going from solid to liquid. And it's boiling. Let's say, I like to say vaporizing or vaporization occurs. Remember, evaporation happens on surfaces, and vaporization happens throughout, but we do also refer to this step as boiling, right? And then, of course, if we're saying that this is going backwards, downward, a cooling curve, right, cooling down, then there's different phase changes that occur. In this case, gas to liquid would be condensation. And this over here would be freezing. So that's a little run through briefly of our thermo unit, and then the last ones that I'll talk about here also are two solid to gas, gas to solid phase changes that we don't really talk about too much, but that we should mention. We do have sublimation, which is going from solid to gas. And then we have deposition, which is the opposite, which is going from gas to solid. All right. So those are just the two other phase changes that could occur in this particular instance. But there is the thermo portion, and almost done.